welcome to this video on alcohols, phenols and functional groups. My name is Chris Harris and I'm from AlleryTutors.com, and this is for the OCR Salters syllabus for the What's in the Medicine topic. And the whole point of this video is basically to go through this part of the What's in the Medicine topic and as a revision. Basically, it's just an overview to give you an idea of what stuff to expect in terms of content that you could find, that you need to know basically, and that you could find in your exam. Now, the slides that I'm using here, they are available to purchase. Really good value for money. You can get the whole series at a reduced price as well. If you just click on the link in the description box, you'll be able to get a hold of them there. Great to enhance your revision material you've already got, and also to help you get that top grade that you need to get into university, etc. So it's all there. By all means, take a look. Okay, so like I say, this is dedicated to OCR Salters, and it matches the specification as you can see here from the syllabus. Okay, so we're going to start by looking at homologous series. So we need to know very specific functional groups that you probably could see in your exams. So the first one are alcohols. Alcohols have the OH group, and what I've done is I've drawn the structural and general formula for both. This is showing the structural because we're showing the bond between them, and this is showing the general formula, which is ROH. They all end in ol. An example is ethanol. Aldehydes, they have this structure here, and they have this general formula, RCHO. End in al, for example, propanal. As you can see there's the end of it. By the way, the R in this bit stands for an ethyl group. An alkyl group. Could be an ethyl, could be a methyl, but it's just an alkyl group. That's what the R stands for. You'll see that a lot. Ketones. Ketones are very similar to aldehydes, except their carbonyl group is in a middle carbon, as you can see. And it has this structure here. The little mark just tells you a different alkyl group to the one over here. Ends in -one. For example, propanone is an example there. Carboxylic acids, they end in COOH. It's a classic sign of a carboxylic acid, and there's how it's drawn as a structural. The suffix, because this goes at the end, is oic acid. So, for example, butanoic acid is this one here. Acid anhydrides, these are quite symmetrical molecules. You've got basically two carbonyl groups sandwiched in between them is an oxygen. And obviously this is the structure of an acid anhydride. They end in oic anhydride. So for example, ethanoic anhydride is this example here. Now you'll notice that obviously we've got two carbons here, but notice we've got double them. Even though we've got four carbons, we don't call it butanoic. We look along one of them strands. They will be symmetrical. Look along one of them strands there, and then you just name it as ethanoic anhydride. So even though you've got obviously double of them, you've got two of them, we just call it ethanoic anhydride. So just be very, very wary of that. You're only looking at one strand. Ethers, this is basically where we've got this oxygen in between two alkyl groups, as you can see here. And these have the word oxy in the middle. So for example, methoxyethane, we've got an ethane bit on the end here and a methane bit or methyl bit here. So we call it methoxyethane in this case. Pretty straightforward. A bit like looks like an oxygen sandwich, a bit like the anhydride. Very nutritious. And esters are basically you have very similar to a carboxylic acid, except instead of the H at the end, you have an alkyl group at the end there. And obviously that's the general formula. Now with this one, you do have a prefix, so it's alkyl something. It's alkyl something anoate at the end. So for example, the alkyl in this case would be methyl, and then this would be ethanoate. And you always name them back to front. So you do methyl, this bit first, then that bit. So it's methyl ethanoate, and that's an ester. Okay, so let's have a look at some alcohols. Alcohols all have that functional group, as you've seen, the OH, which is a hydroxyl group in its homologous series. Now, primary alcohols, they basically have an alkyl group that's attached to a carbon, which is attached to an alcohol. But for it to be primary, the alcohol must be attached to a carbon, which it always will be, which is then attached to one other carbon, which in this case is primary. So, for example, butan 1-ol. Secondary would be the alcohol group attached to a carbon, which is attached to two other carbons, which would make it secondary. So, for example, butan-2-ol. And tertiaries, obviously, you've just got 3 alkyl groups attached to the carbon with the OH on. So this is going to be, for example, 2-methyl propan-2-ol is an example of a tertiary alcohol. Okay, so alcohols, they can be oxidized to aldehydes, ketones, and carboxylic acids. And basically, we use this chemical called potassium dichromate. This is K2CR2O7. It's a mild oxidizing agent. It's reduced itself. Basically, it turns from orange, which is the dichromate ion, to green, which is a chromium ion, Cr3+. Now, primary alcohols, these can be oxidized to aldehydes, and then they go to carboxylic acids. So you can see here, this is an aldehyde. As you can see, we've gone for a primary alcohol. That will form an aldehyde. It has this carbonyl group and a CH on the end carbon, always on the end, and there's an example of it there. And it can be oxidized further to a carboxylic acid. So we get this C double bond O and then OH here. So it's this COOH bit, as we've seen previously in the table. And basically this is an example of a carboxylic acid. So this is, for example, ethanol can be oxidized to ethanal and then to ethanoic acid, for example. Okay, or in this case, this is propanal to propanoic acid. Okay, secondaries oxidize to ketones, and that's what a ketone looks like. So we've got this carbonyl group in the middle this time. Instead of on the end, we've got it in the middle. And so obviously that's an example there. So this is a ketone. So for example, this one would be propanone. Tertiaries, they can't be oxidized by using dichromate. They're not powerful enough. The only way we can oxidize a tertiary alcohol is actually physically burning it. So reacting it with oxygen with a lot of heat. Obviously, you don't produce any valuable products, really. You're just producing carbon dioxide and water if you burn it completely. So, yeah, that's the only way you can oxidize it. Okay, so we can use distillation and reflux in this oxidation process. So let's stick with primary alcohols first. So if we oxidize these, the products produced are dependent on the method that we follow. Okay, and we're going to represent the oxidizing agent as O in a square bracket. You'll see that quite often. So this is a primary alcohol, this one here. We use an oxidizing agent and we form an aldehyde. Okay, then it can go to a carboxylic acid if we're not careful. But it is really difficult to just extract this aldehyde when we're heating it in just a boiling tube, for example. It's really difficult to do that, so we need some specialist equipment. And basically, the specialist equipment is distillation. So we're basically going to remove the aldehyde as soon as it's formed through the oxidation process via distillation. The aldehyde is a lower boiling point than the alcohol, so it will evaporate first. So as long as you boil it at the boiling point of the ethanol, or in this case it's propanol, then we should be able to get your aldehyde. Now, if we oxidize it further, in other words, if we use a reflux instead of distillation, then actually what we do is we form this, and then this oxidizes further to form your carboxylic acid. So we're going to use reflux and excess oxidizing agents, so loads of that, and that's going to make our carboxylic acid. Now, reflux allows strong heating without losing volatile reactants and products. And aldehydes, these can evaporate and they condense back into the flask. So you get this obviously warming here. They've got the cooling of the water running through the outside part of the condenser. Your vapor rises up, your aldehyde condenses and falls back down, reacts again to form your carboxylic acid. And that's basically the principle of how it works. Now, secondary alcohols, these are oxidized to ketones. It's difficult to oxidize ketones further though. So basically, we're just going to use reflux for this. But we are going to use our oxidizing agent, again represented with square bracket O. There's your secondary alcohol. Okay, we're going to use reflux and the oxidizing agent, which is your dichromate. I'm going to use this to make the ketone. And there it is there. So you secondary alcohol, for example, this is propan-2-ol, will make propanone when it's acidified with potassium dichromate. And we just use a reflux setup. Okay, so alkenes, they can be made from alcohols via a solid catalyst, or we can use reflux. Basically what we're doing is just eliminating the water from the alcohol. That's why we call it a dehydration reaction. And we're going to produce an alkene. And And basically one way is the use of acid catalyst, or either sulfuric acid, which is H2SO4, or phosphoric acid, which is H3PO4. Basically we're just going to use the ethanol, mix it with an acid, and we're going to form ethene and water. So this is using an acid. The acid obviously produces H plus ions, which allows this to happen. Another way though is, like say, by passing ethanol vapor over a solid catalyst. So we've got a solid catalyst here, and we've got some mineral wool here soaked in our ethanol, and your solid catalyst will be aluminium oxide, for example. And we're going to use make sure it's in a powder form, so it's a large surface area for the reaction to happen. And basically what we're going to do is going to collect our ethene, which is in the gas form, through an inverted measuring cylinder in a bowl of water. We'll get bubbles of ethene, and the ethene will be trapped in here. So it's just another way of doing it. But notice when we're heating it, we're actually heating the catalyst, so we're generating the heat here. We're not heating this directly. Okay, so we're going to heat the catalyst, and basically it just drifts over. The catalyst is nice and hot, and then it drifts over. Obviously it vaporizes because the tube's getting hot in general, and it allows the reaction to happen. So there you go. That's just highlighting some of the parts of this practical. Okay, so dehydration of alcohols, this can be illustrated using an elimination mechanism, okay, that we need to know. So here we are, we've got our alcohol here, and we're using that acid catalyst. Remember that step, the first one we looked at, we're using either sulfuric or phosphoric. Well, this is where this produces the H plus ions. And basically this comes from the acid catalyst. You've got a lone pair of electrons in the oxygen, in the alcohol, and that moves onto the H plus. And what you're forming is like a water molecule within this full structure. Now, this has a positive charge because oxygen's got far too many bonds. Remember, oxygen can only have 2 bonds. It's actually got 3 on here. So we've got this positive charge in the oxygen. And to stabilize that positive charge, we have the electrons from this bond here move onto the oxygen on here, and effectively it breaks this bond, creating a water molecule. Now, there's the water molecule. Now, you can see here that we now form a carbocation, so we still have a positive charge on our molecule. We're really struggling to get rid of this thing, aren't we? But the carbocation, basically, to get rid of this carbocation, the electrons in this hydrogen here, the electrons in the bond between the carbon and hydrogen here, these move here to form that double bond there, and that basically means that carbon has now 4 bonds. The positive charge will now disappear. And what you're left with is a H plus now floating around freely, and that H plus is your catalyst. Okay, so that is being reformed, and obviously we formed ethene as well, and there's your water because it's a dehydration reaction. Now this is elimination because we are removing a molecule. So when we're going from something like this with no double bond to something with a double bond, we clearly must have eliminated something from the molecule. So look out for them. They're called elimination reactions. Okay, so reacting alcohols with carboxylic acids and acid anhydrides, these are some of the other chemicals that we've seen in that table. These can be used to make esters. So an ester is produced when we react a carboxylic acid with an alcohol, okay, and we have a sulfuric acid catalyst in there. You can just do this in a beaker, to be honest, and it should work. It's reasonably exothermic. You've got to be really careful with the acid because it's quite concentrated. So here's the reaction anyway. And what I've done is I've colour-coded it so you can see where the atoms are going, where they've come from, and where they're going to. There's your carboxylic acid in blue, and your alcohol is in red. We've got an acid catalyst here, and we form an ester. Now what happens is the OH from the carboxylic acid disappears, but the O and the R from the alcohol now bolt onto the carbon, as you can see there. And the hydrogen from the alcohol reacts with the OH from the carboxylic acid, and that forms water. So there is your ester, and there is your water product that you've produced. Notice this is a reversible reaction as well. Now, an ester is also produced when we react it with an acid anhydride, because your acid anhydride is obviously an acid. So let's have a look. Here's your acid anhydride here. This is the one in blue, and the alcohol. And we're going to form an ester. Now, what happens is you can see here you've got the RCOO bit here. From this, and this bit breaks, and the R bit from the alcohol adds on to the end here, so there it is there. And then the rest of the molecule, this bit, the RC double bond O, bonds with whatever's left from the alcohol, which is the OH. So actually what we form here is an ester, but we don't form water. Instead, we actually form a carboxylic acid. So we're just forming slightly different products. But as you can see from the colour coding, it just makes it a little bit easier to see exactly where our atoms are actually joining onto. Okay, alcohols, they react with halide compounds. So for example, HCl, and they form haloalkanes via a substitution reaction. So you can see here we've got the hydroxyl group, which is the OH. It's replaced by the halide ion. So there's the alcohol there, reacting with the hydrogen halide. In this case, we're going to use HCl. This is effectively going to break. Again, I've colour-coded it to see what's going to happen. The OH falls off and is replaced by a chlorine. That's why we call it a substitution reaction. And the OH that was on the alcohol now then goes on to form water. So now you can see here that we formed our haloalkane. Now, this reaction could be done with different alcohols. Obviously, we're using a primary one here. And we get different compounds containing the halide ion as well. That can obviously change the outcome of the product. So, for example, we can use KF as well. So, like salts, for example, instead of just hydrogen-based ones. So, something that contains that halogen, and the reaction is actually just the same. Okay, phenols. Now, phenols, the reason why this is brought in is because phenols actually have an OH group attached to them and still have that hydroxyl group, a little bit like your alcohols, except phenols are a little bit different. They're actually attached to a benzene ring, okay, which is an aromatic molecule. So there's a phenol there, and we have this hexagon shape here. This is the skeletal formula. We have all 6 carbons here, and we have this ring in the middle of delocalized electrons. This is just another example. This is 2-methyl phenol. So what we've done is added another branch onto this. But basically we treat the OH group as carbon number 1 and we number from that. So this one has to be carbon 2 because that's the next lowest number that we can use. So this is 2-methyl phenol, as you can see there. And this is an example of another one. This is obviously a carboxyl group attached to the end here. And actually the proper name for this is salicylic acid, which you may have used in the labs. So this is salicylic acid. Okay, and a test for phenols, this chemical here, all we do is we add iron 3 chloride, and if this phenol exists, we should get this purple colour forming. So there's your iron 3 chloride, and we add your phenol to it, and we get this purpley colour here. So just a little test for seeing if you do actually have a phenol. Now, phenols, they partially dissociate, which means they're actually weak acids, which seems a bit strange, but they are. Now, you can see here, there's our phenol. It's in equilibrium because this is an acid. So they do actually lose this hydrogen, which is a bit unusual because alcohols don't really do that. But this does, and so it loses this hydrogen. Because it gives up some H+ ions, it is actually an acid. But the equilibrium is lying to this side. It's a weak acid, so you don't produce many of these. But we produce this is called a phenoxide ion. Okay, basically it's just a phenol without the hydrogen on. Call it a phenoxide ion. Now, because these are weak acids, they can react with alkalis just like any other acid can, and they form salt and water. So you can see this is sodium phenoxide is produced. This is your salt. So it's phenol plus sodium hydroxide produces your salt. Sodium phenoxide, obviously it loses the hydrogen and it forms water as your product. So it's a neutralization reaction. Carbonates, though, however, they don't react with phenols, whereas strong bases like sodium hydroxide, these do. Your carbonates don't. They're not strong enough as a base compared to sodium hydroxide. And actually, we can use this to our advantage, and we can use this to tell the difference between phenols and carboxylic acids. Because if we have a phenol and we add a carbonate, it won't react. But if we add a carbonate to a carboxylic acid, it will react. So it's basically just a way of distinguishing between the two. Okay, so phenols react with acid anhydrides, okay, but not carboxylic acids. Okay, so let's have a look, see what we get. So this is a reaction with acid anhydrides. Now what they do is they form an ester and carboxylic acid, so they're actually acting as an alcohol in this type of reaction. So it's reacting with the acid anhydrides to do that. However, the reaction with carboxylic acids is different. So despite having that OH group, they don't react with the carboxylic acids to form esters. Okay, you just need to be aware of that distinction between the two reactions. And basically the difference in reactivity that can be used to distinguish between phenols and other alcohols. Okay, so whereas we can distinguish between phenols and carboxylic acids using carbonates, we can distinguish between phenols and alcohols by reacting them with anhydrides and carboxylic acids. They won't react with carboxylic acids, but they will with acid anhydrides. And so that's how we can distinguish between the two. Obviously, alcohols will react with both of them. Okay, and that's it. That's an overview of alcohols, phenols, and functional groups for OCRB salters. Please show your support for this channel by just clicking on the little circle in the middle. All these videos are free to use, and that's really all we need is just your support, just through a subscription. It's all free, so it's just great for your support. And just a reminder that these slides are available to purchase. They're great value for money. Just click on the link in the description box. And it's just another form of revision that you can use, and it all helps to get that A grade or whatever grade you're after in chemistry. But that's it. Bye bye.